You really don't think about the kind of structural violence happening behind your drywall.
Oh, definitely not. Usually not until, a pinhole leak destroys your living room ceiling.
Right. I mean, we just walk through our homes, we turn a handle, and boom, pressurized water instantly arrives.
Exactly, at the exact temperature you want.
Yeah, and we just treat the architecture around us as this static, guaranteed thing, like it's just always going to work.
But it's totally not static. If you actually strip away the plaster, if you look at the physical realities of a modern plumbing system,
It's basically a war zone.
it really is an incredibly hostile environment. You've got differing metal alloys interacting under constant hydrostatic pressure.
And thermal expansion, right? Like stressing the joints every single time hot water flows through them.
Yeah, plus an ever-present risk of galvanic corrosion.
Ah,
It's a dynamic, highly pressurized ecosystem.
which is wild to think about.
It is. And the only reason it appears static to you, the homeowner, is because the original installation was executed with, well, almost a microscopic level of precision.
Because when a system is sealed properly, all that kinetic and chemical energy is perfectly contained.
Right. But achieving that containment requires a mastery of thermodynamics and material science that, honestly, most people just dismiss as blue-collar work.
Which brings us to why we are doing this deep dive today. It's so compelling. We are looking at a raw, highly technical instructional transcript from the YouTube channel How to Plumbing.
Yeah, specifically a masterclass they did titled Solder Copper Pipe Like a Pro, Beginner Mistakes to Avoid.
And reading through this instructor's breakdown, it completely dismantled my preconceived notions of what plumbing actually
Oh,
entails.
for sure. It's eye-opening.
Like, we aren't just talking about turning wrenches or gluing PVC together.
No, not at all. We are talking about utilizing controlled explosions to initiate metallurgical bonding.
Controlled explosions. It sounds like sci-fi.
Well, the instructor provides this phenomenal lens into the trade. He doesn't just show you, where to point the fire.
Right. He breaks down the thermodynamic failures that happen when you point it at the wrong angle.
Exactly. Or even if you hold it there for a fraction of a second too long, it is a really rigorous examination of the physical and chemical thresholds of copper.
And the mission of this deep dive is to extract that underlying science for you. We're going to look at the chemistry of the fluxes, the physics of capillary action.
The destructive reality of electrolysis.
Yeah, and the spatial geometry required to build these systems inside, like a cramped floor joist.
It's a lot, but for anyone listening who has ever tried a DIY plumbing repair and failed,
Which is a lot of us.
definitely, or anyone who just appreciates the unseen engineering of their daily life, this is going to totally reframe how you look at the pipes in your basement.
Okay, let's unpack this. Because before a single flame is ignited, the instructor spends a massive amount of time just on the workbench.
He really does. He insists that the integrity of a joint is actually determined before the pieces ever even touch.
Right, because soldering is fundamentally an exercise in surface preparation.
Yeah, the source text anchors its methodology in this core principle. You cannot force a metallurgical bond.
You can only create the environment for it.
Exactly. You create the perfect environment for one to occur naturally, and the creation of that environment begins with the heat source.
Which is fascinating. The transcript lays out two distinct paths for the torch.
Right, and the choice depends entirely on the operator's understanding of thermal conductivity.
So he contrasts the professional setup,
Yeah.
right, and acetylene tank,
Yeah.
versus this standard, like $20 butane or propane torch you'd find at a hardware store.
And what was your initial thought on that?
Well, my immediate assumption was that professionals use acetylene simply because it burns hotter.
Makes sense.
Yeah, like it melts the metal faster, allowing them to finish the job and move on to the next house. Speed equals money.
And speed is certainly the primary economic driver for a professional, but there is a profound physical consequence to that speed.
Okay, lay it on me.
So acetylene combusts at around 6,000 degrees Fahrenheit when properly mixed with oxygen.
6,000.
Yeah.
Wow.
Propane burns significantly cooler, closer to 3,600 degrees.
Still hot, but yeah, nearly half.
Right. So when you apply an acetylene flame to a half-inch copper pipe, the thermal transfer is incredibly rapid.
The copper reaches the liquidous temperature of the solder in seconds.
Exactly. And this speed actually protects the rest of the piping system.
Wait, how does a hotter flame protect the system?
Because the heat doesn't have time to travel down the pipe and melt adjacent joints, the heat is highly, highly localized.
Oh, I see. It gets in and gets out before
What?
the heat can conduct down the line.
Precisely.
Right.
But the instructor aggressively steers beginners away from acetylene.
Yeah, he insists on the cooler, slower propane torch, which confused me.
Hmm?
If a localized fast heat transfer protects the surrounding system, why force a beginner to use a slower, cooler flame that lets the heat spread?
Because a beginner lacks the ingrained muscle memory to recognize the exact millisecond the pipe reaches the correct temperature.
Ah.
A slower, cooler propane flame intentionally widens the margin of error.
So it gives you a breather to figure out what's going on.
Yeah, it provides a larger temporal window to observe the physical changes in the copper and the flux. If a novice uses acetylene,
They'll just vaporize the whole thing.
they will almost certainly push the copper past the ideal temperature zone before they even realize what's happening.
Right.
The propane torch acts as a governor on the thermal input. It prioritizes control over efficiency.
You're trading efficiency for a larger thermodynamic sweet spot. That makes total sense.
It does.
But, okay, even with the thermal input perfectly calibrated, the instructor makes it super clear the heat is totally useless if the surface isn't physically ravaged first.
Yes, ravaged is the right word.
This is the part of the text that really challenged my understanding of how metals interact. The instructor mandates this incredibly aggressive cleaning regimen.
Using 1/2 inch and 3/4 inch wire brushes.
Yeah, for the inside of the fittings. And emery cloth, which is basically sandpaper for the outside of the pipes.
It is the most critical mechanical step in the entire process. He is adamant about taking the copper down to a raw, deeply scratched finish.
But here's where my logic was totally flawed.
Okay, tell me.
If I have a piece of copper that looks perfectly shiny and clean, right off the hardware store shelf,
Right.
and I am about to bathe it in a highly acidic chemical paste and hit it with a 3600-degree blowtorch,
Yeah.
why am I spending 10 minutes manually scrubbing it with abrasive wire? Wouldn't a 3600-degree flame instantly incinerate any microscopic dust or oil on the pipe anyway?
Well, you're not wrong about the oils. It would incinerate oils and organic compounds, yes.
So why the scrubbing?
Because the enemy of a solder joint isn't dust. It's the atomic structure of the copper itself.
The copper itself is the enemy.
Yes. Copper is highly reactive. The moment a freshly manufactured copper pipe is exposed to the atmosphere, the surface atoms react with oxygen.
Oh, like rust on iron.
Exactly. But on copper, it forms a thin, invisible layer of cuprous oxide. This oxidation layer is essentially a chemical force field.
A force field.
Yeah.
And the solder can't penetrate that field.
Solder physically cannot bond to an oxide.
At all.
Not at all. A solder joint is not like hot glue sitting on top of cardboard.
Okay.
It is an intermetallic bond. The liquid tin in the solder must physically dissolve a microscopic layer of the solid copper to form a new hybridized metal alloy at the boundary layer.
Wow, so they literally merge into a new metal.
Yes. And if there is a barrier of cuprous oxide in the way, the liquid solder will simply bead up and roll off the pipe.
Like rain on a freshly waxed windshield.
Exactly like that.
Right.
Furthermore, your assumption about the torch burning off the impurities, it's actually the inverse of reality. Applying extreme heat to copper radically accelerates the oxidation process.
Wait, really? So the flame isn't cleaning the pipe, it's actually feeding the oxygen reaction.
Yes, it thickens the protective barrier.
Oh my God.
So when the instructor emphasizes the wire brushes and the emery cloth, he is not telling you to polish the pipe.
He's telling you to perform a brutal physical excavation.
That's exactly it. You are tearing away the reacted atoms to expose the virgin, unreacted copper lattice underneath.
Just ripping it down to the raw material.
And by scratching the surface with the abrasive cloth, you are also dramatically increasing the microscopic surface area.
Because of all the little gouges from the sandpaper.
Right. It provides thousands of tiny physical ridges for the liquid metal to bite into.
Okay, so we aren't just cleaning a canvas. We are intentionally roughing it up so the paint has something to hold on to.
That's a perfect analogy.
And the text briefly notes that this excavation process is often happening in terrible conditions, right?
Oh, yeah. The instructor points out the necessity of having mini cutters on hand.
Those tiny ratcheting pipe cutters.
Which really hints at the reality that you aren't always doing this comfortable excavation at a nice workbench.
Right, you are doing it wedged behind a toilet or inside a dark wall cavity.
The spatial constraints absolutely dictate the tooling. We will explore the geometry of those tight spaces later, but the fundamental chemistry remains identical.
Whether you are in a brightly lit workshop or a dark crawl space, the oxide layer must be destroyed.
Period.
Right. So we physically excavated down to the raw copper lattice. But as you just said, the moment oxygen and heat hit that bare metal, the oxide layer instantly begins to reform.
Instantly.
So how do we keep the copper raw long enough for the solder to melt into it?
This brings us to the chemical catalyst of the entire operation.
The flux.
The flux, it's the chemical intermediary that bridges the gap between the mechanical preparation and the thermal application.
And the text highlights the extreme care required when handling it.
It does. But it presents what looks like, well, a glaring contradiction.
Yeah, I noticed that too. The instructor is applying this acidic paste to both the outside of the freshly sanded pipe and the inside of the fitting.
And as he is brushing it on, he explicitly states, there is no such thing as too much flux.
Right, he wants a heavy, generous coating.
Yeah.
But then, the very second he pushes the pipe into the fitting, his tone completely shifts.
He aggressively warns the viewer to take a rag and meticulously wipe away every single drop of excess flux that squeezes out of the joint.
It seems so hypocritical.
Yeah.
Like, use a ton, but also get rid of it immediately.
Well, what's fascinating here is, to understand the instructor's apparent hypocrisy, you have to understand the chemical life cycle of the flux.
Okay.
It serves two distinct sequential purposes. Cold, right out of the jar, the flux acts as a mild acid.
Okay, so it's acidic.
Right. It actively etches the copper, chemically dissolving any trace amounts of cuprous oxide you might have missed with the emery cloth.
Oh, so it's a chemical backup to the physical sanding.
Precisely. But its primary function activates when the heat is applied.
When you hit it with the torch.
Yes. As the temperature rises, the flux melts and spreads out, coating the raw copper atoms.
Okay.
In this liquid state, it acts as an impenetrable oxygen barrier.
So it physically blocks the atmospheric oxygen from reaching the hot copper.
Exactly. Completely preventing the rapid heat-induced oxidation we discussed earlier.
Wow.
Inside the microscopic gap between the pipe and the fitting, you desperately need total, uncompromised coverage of this protective barrier.
Therefore, during application, there is no such thing as too much.
Right. You want that gap totally flooded with flux.
That explains the generous application. But why the immediate frantic cleanup on the outside of the pipe?
Well, he warns that if you don't wipe away the squeeze out, you'll have solder running everywhere.
Yeah. And more concerningly, he mentions that the pipe will turn a crusty green over time.
Because that protective barrier is still a highly corrosive acid.
Oh, right.
If you leave a glob of active flux sitting on the exterior of a copper pipe, hidden in a dark, damp wall cavity, it doesn't stop working. It continues to etch the metal.
It just keeps eating away at it.
Over months and years, the acid reacts with the copper to create cupric salts.
Is that the green stuff?
Yeah, that bright, toxic-looking green crust known as verdigris. Eventually, that slow-motion chemical reaction will eat a pinhole straight through the wall of the pipe,
Causing a catastrophic leak.
Yes.
So the very chemical responsible for ensuring the joint doesn't leak today is the exact chemical that guarantees it will fail a decade from now if you are sloppy.
It is the ultimate chemical double-edged sword.
That is terrifying.
It is. And the instructor's warning about the solder running everywhere, that touches on a really fascinating property of fluid dynamics.
Okay, how so?
Molten solder has an incredibly high affinity for active flux. The liquid metal is chemically drawn to it.
Oh, I see where this is going.
If you have a streak of flux running 2 inches down the outside of your vertical pipe,
The moment the solder liquefies, it will follow that streak right out of the joint.
exactly, right down the outside of the pipe, starving the actual connection of metal.
I see. The flux acts as a chemical rail system. The liquid metal is the train, and it has absolutely no choice but to follow exactly where you laid the tracks.
That is an excellent way to visualize the wetting process.
And if you leave tracks running down the outside of the pipe, the train derails.
You must control the boundaries of the chemical track to control the flow of the metal.
Man, that's so cool. And the text is extremely specific about the metal we are actually using as the train.
Yeah.
It mandates the use of lead-free solder, usually stamped 95.5.
Right, 95.5.
We all know the historical context here, right?
Right.
Plumbers used to use 50-50 solder.
Half tin, half lead.
Yeah, which was incredibly malleable and easy to melt. But obviously, because of the devastating neurological effects of lead leaching into drinking water, the industry was legally forced to pivot.
Absolutely necessary for public health.
But beyond the public health victory, the shift to 95.5 lead-free, I mean, it fundamentally changed the difficulty of the job, didn't it?
Oh, drastically. 95.5 signifies an alloy of roughly 95% tin and 5% antimony.
Okay.
This alloy behaves very, very differently under a flame than the old leaded solder.
In what way?
Leaded solder had a very wide plastic range, meaning there was a large temperature window where it was in a mushy, workable state before turning completely liquid or completely solid.
So it's incredibly forgiving for beginners.
Extremely.
Yeah.
But 95 tin antimony solder has a much higher liquidus temperature and a very narrow plastic range.
So it goes from solid to liquid fast,
It transitions from solid wire to watery liquid almost instantly.
meaning you have to be vastly more precise with your heat.
Yes.
Which brings us to the actual execution. We have an excavated copper surface. We have an acidic flux barrier precisely applied.
Yeah.
We have our 95.5 lead-free wire ready.
The pipe and the fitting are put together.
Yeah. This is where the transcript dives into the real-time physics of the operation, and it immediately highlights the most counterintuitive aspect of soldering.
The application of the flame is where amateur logic consistently fails.
Exactly. If my goal is to melt a stick of metal into a gap, my instinct, and I think anyone's instinct, is to point the blowtorch directly at the stick of metal.
Naturally.
Melt it like a candle, let it drip into the crack.
But the instructor treats this as the ultimate cardinal sin.
He repeats over and over. You do not heat the solder. You heat the fitting and the pipe.
Right. But why?
If you apply a 3600-degree flame directly to a thin wire of tin antimony, the alloy will instantly liquefy, overheat, and basically drip aimlessly onto the floor.
Splash everywhere.
Right. You aren't trying to melt metal onto a surface. You are trying to draw metal into a microscopic void.
And to achieve that, you must leverage the physics of capillary action.
Exactly. The source text operates on one immutable physical law. Solder is drawn to the heat. Okay, I understand capillary action in biology, right? Like plants pulling water up through their xylem.
Good analogy.
But how does that physical mechanism translate to heavy liquid metal flowing between two solid copper pipes?
The physical principles are identical. Capillary action is driven by the relationship between cohesive forces.
Meaning the liquid metal atoms wanting to stick to each other.
Right, and adhesive forces. The liquid metal atoms wanting to stick to the copper surface.
Okay.
The gap between a standard half-inch pipe and its fitting is engineered to be incredibly tight. We're talking usually just a few thousandths of an inch.
So it's essentially a vacuum waiting to happen.
Precisely. When the operator applies the flame to the back of the fitting, the copper, being a phenomenal thermal conductor, rapidly absorbs and distributes that heat.
The whole thing gets blazing hot.
The entire fitting reaches the melting temperature of the solder. Then, the operator takes the cold solder wire and touches it to the front of the joint, entirely opposite the flame.
And because the copper is so hot, the copper itself acts as the heat source to melt the solder wire.
Yes. The hot copper instantly breaks down the solid state of the wire. And because liquid metal naturally flows toward the highest temperature gradient.
Toward the flame at the back.
Yes. And because the adhesive forces of the molten tin aggressively seek to bond with the etched copper lattice, the liquid solder is sucked straight into that microscopic gap.
Defying gravity in the process.
Totally defying gravity.
If I heat the top of a fitting and touch the solder to the bottom lip, the heavy liquid metal will be pulled aggressively upwards, filling the void.
It will wick entirely around the circumference of the joint, drawn by the thermal gradient and following the chemical track laid by the flux.
That is just wild.
But this elegant fluid dynamic only occurs if the copper is the heat sink that melts the metal. If the torch melts the metal, the capillary engine stalls.
The engine stalls. That is a brilliant mechanical dance, but I mean, it requires an insane level of sensory awareness.
Oh, absolutely.
You are blasting a pipe with fire, and you need to know the exact fraction of a second. The entire piece of copper hits the liquidus temperature of the 95 alloy.
And there are no digital thermometers on the pipe.
Right. So how does the instructor know when to feed the wire?
The transcript details a reliance on specific auditory and visual cues. The professional plumber doesn't guess. They read the reaction of the materials.
Auditory cues over a blowtorch.
Yeah. The first cue comes from the flux. As the copper heats up, the flux begins to boil and smoke. It produces a distinct sizzling sound.
Like bacon in a pan.
Exactly. That auditory cue tells the operator the temperature is rapidly approaching the threshold.
And then they begin probing the joint with the wire.
Correct. The operator will repeatedly tap the tip of the cold solder wire against the lip of the heated joint. Tap, tap, tap.
To Cestian.
While the copper is too cold, the wire will just bump against it. But the instant the copper reaches the critical temperature, the solid wire will stop bouncing.
It will just melt.
It will instantly liquefy and flash into the joint. The instructor describes watching for this visual confirmation. A brilliant, mirror-like silver ring that suddenly appears around the seam.
The silver flash.
The silver flash! It's the visual proof that surface tension has broken and capillary action is actively pulling the metal into the void.
And the moment you see that flash.
You pull the flame away immediately.
But let me challenge the timing aspect here.
Sure.
If achieving the melt is the only goal, and hot is good, why is the exact timing so critical? Why wouldn't a beginner just blast the joint with a torch for an extra 30 seconds to absolutely guarantee the entire fitting is scorching hot?
To be safe, you mean?
Yeah.
Yeah.
Why risk a cold joint when you could just overpower it with heat?
Because overpowering it triggers a catastrophic chemical failure.
Really?
Overheating is the second most common beginner mistake detailed in the text, and it is arguably more destructive than underheating.
How is it more destructive?
Well, we established that the flux is a chemical barrier, right?
Yeah, it's an organic acid paste.
But it has a strict thermal limit. If you push the temperature of the copper too high, the flux doesn't just boil, it burns.
It catches fire.
It scorches and undergoes thermal decomposition. It carbonizes into a hard black scale inside the joint.
Okay.
And the moment the flux carbonizes, it loses all of its protective properties, the barrier drops, and the extreme heat instantly oxidizes the raw copper underneath.
So you've completely undone the mechanical excavation and the chemical etching in a matter of seconds.
Worse than undone. You've introduced a permanent carbon layer.
And solder won't stick to carbon.
Molten solder fundamentally cannot bond to carbon or oxidize copper. When the liquid metal hits that burned flux, it stops dead.
The capillary wicking fails.
The joint is compromised, and it will inevitably leak under pressure.
Can you just brush more flux on it?
No, there is no chemical fix for this. You cannot just add more flux. You have to physically cut the burned joint out of the plumbing system, throw away the fitting, and start the entire process over with fresh pipe.
That perfectly illustrates the tightrope walk. It is a strict thermodynamic Goldilocks zone.
Exactly.
If you are 50 degrees too cold, the solder beads up and falls to the floor. If you are 50 degrees too hot, you bake the flux into a carbon shield and ruin all the materials.
Which is exactly why the instructor initially recommended the slower propane torch for beginners.
Bringing it full circle.
It expands that Goldilocks zone, giving the operator time to hear the sizzle of the flux and see the silver flash of the solder before the system overheats.
That is amazing. And, the operation doesn't even end when the torch turns off.
No, it doesn't.
The text highlights a vital final step. The cleanup wipe. The instructor is adamant about taking a thick, dry cotton rag and aggressively wiping the joint while the metal is still semi-liquid and the pipe is radiating intense heat.
Yeah, he frames it as making the joint look pro by removing the drips.
But based on our discussion about the verdigris in the active acid, this isn't just about aesthetics, is it?
Not at all. Aesthetics are just a byproduct of correct chemical management.
Okay, so what's the real reason?
Wiping the hot joint serves two critical structural purposes. First, it smooths the cooling metal, removing heavy droplets that could solidify into sharp burrs.
Which you don't want.
Right. But more importantly, the heat makes the remaining flux on the outside of the pipe highly viscous.
Like syrup.
Yeah. Wiping the hot pipe completely removes the residual acidic flux before it can cool, harden, and begin its slow, decade-long process of eating through the copper wall.
It's the final stabilization of the microclimate.
Beautifully put.
So that covers the pure physics and chemistry of a basic, straight copper-to-copper joint. But a house's plumbing system isn't an endless series of straight pipes.
Far from it.
The network has to interface with appliances, valves, and distinctly different materials. And this is where the transcript moves from basic thermodynamics into advanced system protection.
Connecting copper to different materials requires an understanding of how distinct elements interact over time, particularly in an aqueous environment.
An aqueous environment, meaning water.
Right. The instructor details a scenario where the copper pipe must connect to the hot water heater, which is traditionally constructed of galvanized steel.
And he introduces a highly specialized fitting for this connection called a dielectric union.
Yes.
He doesn't just thread the copper directly into the steel tank. The text implies that doing so would be disastrous.
I want to unpack the why here, because this goes beyond just leaking water. This goes into the realm of destructive electrical phenomena.
It really does. If you thread a copper pipe directly into a steel water heater, you inadvertently construct a low-voltage short-circuited battery inside your plumbing system.
Wait, a battery? How does plumbing become a battery? There are no wires attached.
The destructive force at play here is galvanic corrosion, often referred to in the trade simply as electrolysis.
Okay, but how does it work?
It requires three components to form a galvanic cell. You need two dissimilar metals with different electrode potentials and a conductive electrolyte connecting them.
Okay.
In the galvanic series, copper is a noble cathodic metal. Steel is an active amidic metal. So they are electrically opposite.
Very much so. When you physically thread the copper pipe into the steel tank, you create the metallic pathway. The water flowing through the pipes, which contains dissolved minerals and ions, acts as the electrolyte.
So the water completes the circuit.
Yes. The moment the water bridges the two metals, electrons begin stripping away from the active steel anode and flowing through the water to the noble copper cathode.
Oh,
The instructor graphically describes the electrons trampolining between the metals.
trampolining electrons. I love that image.
It's vivid. And as the steel donates its electrons, it undergoes rapid, aggressive oxidation. The physical structure of the steel literally disintegrates.
It rusts itself to death from the inside out.
At a highly accelerated rate, the steel threads will turn to mush and violently fail, often causing a catastrophic flood and completely destroying the water feeder.
Just because two metals touched? That is insane.
To prevent this invisible electrical decay, the industry utilizes the dielectric union.
And the design of the dielectric union is pure mechanical isolation, right?
Yeah.
Exactly.
It's a two-part fitting. One half is made of brass, which safely solders to the copper without triggering extreme galvanic action.
Correct.
The other half is steel, which threads safely into the water heater. But the magic is the physical barrier placed between them. A hard plastic sleeve and a thick rubber washer.
Right. When you tighten the union, the plastic and rubber electrically isolate the brass from the steel.
No metallic contact, no electron flow, no battery.
It breaks the circuit perfectly. But as the text points out, the installation of this fitting introduces a massive logistical hurdle.
I can guess what it is.
Go for it.
You have to solder the copper pipe into the brass half of the union. And we just spent 30 minutes establishing that soldering requires rapidly heating the brass to several hundred degrees.
Right. If you hit that union with a torch while the plastic sleeve and the rubber washer are inside,
You will instantly melt the safety mechanisms into a puddle of toxic slag,
completely ruining the seal.
which necessitates a strict procedural rule in advanced plumbing, which the instructor highlights, the teardown technique.
Yes, the teardown.
Before the torch is even ignited, the operator must completely disassemble the dielectric union, carefully remove the delicate plastic insert and the rubber washer, and set them far away on the workbench.
You essentially have to gut the fitting to protect it from your own process.
It's like performing surgery.
It is. You isolate the bare brass piece, apply the flux, fit the copper pipe, and execute the solder joint. You establish the watertight bond while the fitting is entirely empty.
And then comes the discipline of patience, because brass has a massive thermal mass.
Brass retains heat exponentially longer than thin-walled copper. If an amateur solders the fitting, turns off the torch, and immediately attempts to reassemble the union,
The residual heat melts the plastic anyway.
the thermal energy radiating off the brass will melt the plastic sleeve just as surely as the direct flame would have. The operator must let the entire assembly ambiently cool to room temperature before reinserting the plastic and rubber isolators.
It is a phenomenal order of operations. And the instructor expands this teardown logic to other vulnerable components, specifically valves.
Valves are tricky.
A plumbing system relies on ball valves to shut off the water, and pressure relief valves to prevent water heaters from exploding. These valves utilize internal nylon or Teflon seats to create their watertight seals.
Right.
But you can't always take a factory-sealed ball valve apart to protect the Teflon while you solder it to the pipe.
No, the construction of a ball valve usually prevents internal teardowns, so the operator must utilize thermal management strategies. The transcript details two specific approaches.
Okay, what's the first one?
The first relies purely on spatial heat management and flame control.
The instructor talks about the angle of attack. He says you must aim away from the handle.
You are consciously manipulating the thermal gradient. By directing the tip of the inner blue cone of the flame specifically at the bottom cup of the fitting,
Okay.
and angling the torch so the excess heat washes down the pipe rather than up into the valve body, you prevent the core heat from migrating to the Teflon seat.
So you are utilizing the conductivity of the copper to melt the solder before the ambient heat can destroy the valve above it.
It's a race against thermal conductivity.
But the instructor acknowledges that sometimes the space is just too tight to control the angle of the flame. Like if you are backed into a corner, you can't always aim away from the handle.
Exactly. So he offers a second, much safer strategy, pre-soldering a stub.
The stub method. This is the ultimate protective measure.
It really is. Rather than trying to execute a complex, high-risk joint inside the wall, the operator takes a short, 6-inch piece of copper pipe, the stub, and solders it into the valve while standing at a comfortable workbench.
Where they have total control of the angles, perfect lighting, and zero spatial constraints.
Precisely. Once that stub is securely soldered into the valve and completely cooled, the operator takes the entire assembly to the installation point.
And now,
Now, when they solder the assembly into the main water line, the torch is applying heat 6 inches away from the sensitive Teflon seat. The length of the pipe acts as a physical thermal buffer, dissipating the heat before it can reach the valve body.
you are using distance to outsmart the thermodynamics. And this idea of navigating spatial constraints acts as the perfect pivot into the next major theme of the transcript.
Oh, this is where it gets really interesting.
Because everything we've discussed, the precise application of flux, the delicate reading of the silver flash, the teardown of the unions,
Yeah.
it all assumes a level of physical control that rarely exists in residential plumbing.
The theory of fluid dynamics and metallurgy works perfectly in a well-lit laboratory. The reality of residential plumbing occurs inside dark floor joists, cramped crawl spaces, and bizarre architectural angles.
The environment itself becomes an active, hostile variable in the soldering equation.
The transcript vividly illustrates this when the instructor is attempting to run a water line up into a bathroom. He notes the specific danger of working between the floor joists, stating that you really don't have anywhere to play.
You are wedged between ancient, bone-dry structural lumber, and you are holding a tool that spits a continuous 3,600-degree flame.
The spatial constraints elevate the process from a simple mechanical task to an extreme fire hazard.
A slight miscalculation in the angle of the torch, or even a momentary loss of balance,
Will result in the direct application of a combustion flame to the combustible framing of the house. The operator is forced to constantly monitor the thermal reflection off the wood while simultaneously monitoring the capillary action of the solder.
It requires an intense, almost isometric physical focus.
It's exhausting.
And the solution the instructor provides to this spatial nightmare isn't just, be more careful with the fire. It's a total strategic pivot.
He introduces the concept of prefabrication,
Prefabrication.
which is the hallmark of an experienced tradesman. When the physical environment is too hostile, too cramped, or the geometry of the pipes is just too complex to safely operate a torch, the operator stops attempting to force the work into the space.
What do they do instead?
They mathematically map the space and bring the work out into the open.
The instructor literally measures the exact geometry required to navigate the joists.
Yeah.
Every angle, every drop, every turn. And then he steps completely away from the ceiling.
He sits down on the open basement floor and begins assembling this intricate, multi-piece copper puzzle.
He fluxes and solders 5 or 6 different joints simultaneously on the floor, where he has 360 degrees of access, 0 fire risk, and total control over the thermal application.
He is building ship-in-a-bottle architecture. By constructing a rigid, complex subassembly on the floor, he limits the number of extreme risk joints he has to perform up in the air.
He lets the entire prefab piece cool and then lifts it up into the joists as one solid unit.
Exactly.
But even with brilliant prefabrication, you eventually hit a wall. You still have to connect that newly built assembly to the existing rigid pipes already anchored in the ceiling.
And the transcript highlights a massive geometric problem here.
The rigid pipe constraint.
Yes, standard copper plumbing relies on rigid geometry. A standard coupling, which is the small sleeve used to connect 2 straight pipes together, has a tiny physical indent, or a stop, rolled right into the middle of its interior.
Right. You push the left pipe in until it hits the stop. You push the right pipe in until it hits the stop. You solder it. It guarantees perfectly even insertion depth.
Yes, that's the ideal scenario.
But the instructor points out a scenario where you have 2 rigid pipes firmly anchored to the framing exactly 6 inches apart. You need to bridge that gap.
But because the pipes are rigid, you cannot pull them back to wedge a standard coupling with an internal stop between them. The pipes literally won't bend.
You cannot alter the geometry of the existing infrastructure.
This is the exact scenario the slip coupling was engineered to solve.
A slip coupling.
A slip coupling is visually identical to a standard coupling, but it completely lacks the internal dimple. The bore is perfectly smooth from end to end.
And the mechanical advantage of a smooth bore is brilliant. Because there is no internal stop, you can take the slip coupling and slide it entirely up and over one of the fixed pipes, pushing it completely out of the way.
You essentially park the fitting on the existing line. Then you bring your new 6-inch prefab piece into the space, aligning it perfectly flush with the existing pipe.
And because the coupling is parked out of the way, you can achieve perfect lateral alignment without bending the copper.
And once the pipes are aligned, you simply grab the slip coupling and, like pulling down a sleeve, you slide it back down the pipe until it evenly bridges the gap across the two fixed ends.
You've closed the physical system without having to force or bend the structural piping.
You apply the flux, hit it with the torch, and capillary action seals the deal.
It is a mechanical manipulation of space that elegantly bypasses the rigid constraints of the material. It perfectly encapsulates how plumbing requires an equal mastery of chemistry and spatial puzzle solving.
It really is a puzzle.
And this reality of navigating existing rigid infrastructure transitions us perfectly into the final and undoubtedly most surprising act of the transcript.
Oh, this part is wild.
Because residential plumbing doesn't exist in a modern vacuum. Plumbers are constantly interfacing with history.
Every time an operator opens a wall cavity in a home built before the 1980s, they're essentially performing architectural archaeology. The materials, the dimensions, and the legal codes reflect the exact era of installation.
The instructor runs headfirst into this historical collision. He encounters an existing water supply line protruding from the ceiling that is made of 3/8-inch soft copper.
Yeah.
Throughout the entire video, he has been utilizing rigid 3/4-inch copper pipe. He is suddenly faced with connecting a tiny, decades-old supply line to a massive, modern appliance.
This is an encounter with grandfathered code and fluid dynamics. In the mid-20th century, running 3/8-inch soft copper was common practice for residential water lines.
Why?
The material was cheaper, and because it came in malleable rolls, it was incredibly easy for installers to snake through walls without needing to solder elbows at every turn.
But the laws of fluid dynamics dictate that a 3/8-inch pipe can only carry a fraction of the water volume that a 3/4-inch pipe can.
Exactly. Modern plumbing codes recognize that a 3/8-inch internal diameter cannot provide sufficient volumetric flow for modern, high-demand fixtures.
Right.
If you attempt to feed a modern, high-capacity water heater with a 3/8-inch line, you will starve the appliance, drastically dropping the pressure across the entire house when multiple fixtures are opened.
So current building codes almost universally mandate a minimum of 3/4-inch pipe for the main branches feeding a water heater.
They do. So the instructor is forced to bridge this legal and physical gap. He can't repipe the entire house on this single service call, obviously.
So he utilizes a series of reducers, these stepped copper fittings, to transition the tiny 3/8-inch pipe up to a 1/2-inch, and then from 1/2-inch up to the required 3/4-inch connection at the water heater.
He creates a hydrodynamic funnel. While it doesn't solve the underlying volumetric restriction hidden deep in the walls, it safely and legally interfaces the old architecture with the modern appliance demands.
But a sizing transition is relatively straightforward physics. The transcript immediately plunges into a material transition that sounds like it belongs in the 19th century.
Oh, the wipe joint.
Yes. The instructor moves away from the pressurized water lines entirely and looks at the drainage system beneath his sink. He is tasked with connecting a modern, shiny, chrome-plated P-trap, the curved pipe designed to hold water and block sewer gases,
Right.
to an ancient, heavy branch drain pipe sticking out of the wall, which appears to be constructed of antiquated brass or lead.
This presents a monumental chemical and metallurgical challenge. You cannot utilize the capillary licking of 95 lead-free solder to connect these materials.
Why not?
Chrome plating is highly engineered to be chemically resistant and incredibly smooth. The molten tin will simply run right off it. Furthermore, modern lead-free solder does not possess the correct metallurgical affinity to bond effectively with old oxidized lead drainage pipes.
The modern techniques just fail completely.
They fail completely.
And this is where the instructor reintroduces the very element we celebrated removing earlier, lead.
Lead makes a comeback.
He explicitly states that to make this specific connection, the operator must purchase a massive, heavy bar of 60/40 lead, an alloy consisting of 60% tin and 40% lead. I have to admit, Seeing him enthusiastically bring toxic lead back into the process felt incredibly jarring after learning about the strict 95 mandates.
It is a critical distinction of application, governed by strict isolation protocols. The absolute ban on leaded solder applies exclusively to potable water systems.
The pressurized network that carries the water you actively ingest, cook with, and bathe in.
Right. The P-trap under a sink is a localized, non-pressurized drainage component. It exists solely to funnel contaminated wastewater out to the municipal sewer.
The wastewater never flows backward into the drinking supply.
Never. The systems are physically segregated. Therefore, the use of heavy lead alloys in this highly specific, isolated drainage context is legally permitted, and historically, it is the only mechanically viable method to bridge these archaic materials.
Okay, the context of wastewater justifies the material. But the physical process he uses to apply this lead alloy is wildly different from the elegant, hands-off capillary wicking we spent the first half of the deep dive dissecting.
Very different.
It is an aggressive, tactile process known as a wipe joint, and it starts with brutalizing the modern chrome.
Because the chrome plating rejects chemical bonding, the operator must completely eradicate it.
The instructor takes a heavy, coarse steel file and violently grinds the shiny chrome plating completely off the end of the P-trap,
He physically destroys the aesthetic finish.
filing deep into the metal until he exposes the dull, yellowish, raw brass core hiding beneath the plating.
It is the ultimate form of physical excavation, far more aggressive than the emery cloth used on the copper. He must reach the base metal to give the heavy lead alloy a surface it can mechanically key into.
Once he has the raw brass exposed, he applies the flux. But he doesn't use the thin, precise wire of solder. He takes the massive bar of 60/40 lead and hits it with the torch.
But he isn't trying to melt the metal into a liquid state so it can wick into a microscopic gap.
Right, he is intentionally trying to create a massive, thick blob of semi-melted lead encompassing the entire exterior of the connection.
The choice of the 60/40 alloy is paramount here. We discussed how modern 95/5 solder turns into a watery liquid almost instantly.
Yeah.
60/40 lead operates differently. Because it is close to a eutectic composition, but not quite perfect, it possesses an incredibly broad plastic range.
Okay, so it gets mushy.
When heated, it doesn't immediately liquefy. It transitions into a thick, mushy, semi-solid paste. It behaves exactly like heavy metallic clay.
And because it acts like clay, the instructor treats it like clay. He doesn't just apply heat and step back.
Yeah.
The transcript describes him taking a thick, heavily folded cloth, which he refers to as a rank or a wiping cloth,
Yeah.
and physically grabbing this massive blob of 400-degree semi-molten lead with his rag-covered hand.
He uses the thick cloth as a thermal barrier for his hand, while utilizing the pressure of his palm and fingers to physically smear, shape, and sculpt the heavy, hot metal smoothly around the entire circumference of the joint.
It is literal metallurgy by hand. He is wiping the molten metal over the raw brass and the old drain pipe, forcing the mushy lead to bridge the gap through sheer physical pressure.
It's an incredibly visceral, brute force method of creating a mechanical seal where the delicate precision of capillary action is impossible.
It relies entirely on the tactile feedback, the internal rhythm, and frankly, the pain tolerance of the operator.
Totally. The wiped joint is arguably the oldest technique in the entire plumbing trade, dating back centuries, but it introduces an obvious structural flaw.
Which is exactly what I was thinking. If you are hand-smearing mushy metal around a pipe, relying solely on your physical grip rather than the natural physics of capillary wicking, how on earth do you guarantee the seal is watertight?
Human hands aren't perfect.
Right. You are inevitably leaving tiny, invisible pores, grain boundaries, and microscopic voids within that smeared lead.
And in plumbing, microscopic voids are catastrophic. Even on a non-pressurized drain, water will eventually seek out those imperfections. The joint will weep, and the trap will leak. The wiped joint requires a secondary sealing mechanism to compensate for the inherent porosity of the hand-shaped metal.
And the instructor's solution to this porosity is perhaps the most elegant, unexpected piece of alchemy in the entire transcript. It feels straight out of the 1800s.
It is a brilliant application of phase changes.
He takes a completely normal, everyday wax candle, like a cheap, white emergency candlestick you'd find in a kitchen drawer.
Yeah.
The wiped lead joint is still radiating intense thermal energy, hundreds of degrees. He takes the candle and aggressively rubs the solid wax directly over the surface of the hot, smeared metal.
The residual heat of the lead instantly breaks down the solid wax, turning it into an incredibly thin, highly viscous liquid. And this is where a different secondary form of capillary action takes over.
The liquid paraffin wax wicks directly into the metal.
Precisely.
Wow.
Because the liquid wax is so thin, it acts as a penetrating fluid. It is aggressively drawn into every microscopic pore, every grain boundary, and every invisible void left behind by the wiping process.
This is just incredible.
The wax physically permeates the outer layer of the lead structure. As the entire joint finally ambiently cools to room temperature, that penetrating wax solidifies deep inside the microscopic architecture of the metal.
Creating an absolutely impregnable, watertight seal. You are literally sealing a plumbing system with candle wax.
It's amazing.
It's an incredible juxtaposition. We started this deep dive talking about the precise chemical limits of synthetic acid fluxes and the thermodynamic laws of modern lead-free alloys.
And we end it watching a guy smear molten lead with a rag and seal it with a Campbell stick. It perfectly illustrates that plumbing is an evolving historical record. To be a successful operator, you must possess a rigid understanding of modern chemistry and thermodynamics to handle new materials safely.
But you also have to know the old tricks.
You must retain the tactile, artisan tricks of the past, because the reality of residential architecture guarantees you will inevitably encounter both eras within the exact same wall cavity.
So, we've unpacked an immense amount of hidden science from a transcript that presented itself as a simple DIY video. We explored the thermodynamic differences between acetylene and propane and how thermal input dictates the operator's margin of error.
We examined the brutal physical excavation of cuprous oxide required to expose the virgin atomic lattice of the copper, proving that heat alone cannot bypass chemical reality.
We dissected the chemical paradox of the flux, how a corrosive acid is utilized to protect the metal from the very heat designed to bond it, and the long-term destructive consequences of verdigris if that acid isn't meticulously managed.
We explored the physics of capillary action, detailing how cohesive and adhesive forces conquer gravity to draw liquid metal into microscopic voids, confirmed only by the visual cue of the silver flash.
We looked at the devastating electrical reality of galvanic corrosion and how the dielectric union utilizes plastic and rubber to physically break the battery circuit, necessitating the intense procedural discipline of the teardown technique.
We examined the spatial geometry of prefabrication to bypass the fire hazards of cramped floor joists, and how the slip coupling subverts the rigid constraints of existing architecture.
And finally, we witnessed the collision of modern code and historical infrastructure, transitioning from volumetric flow calculations to the lost art of the wipe joint, utilizing the specific plastic range of 60-40 lead and the capillary action of paraffin wax to bridge the mechanical gap.
It forces a total recalibration of how we view the trades. The next time you look at the infrastructure of a home, you shouldn't just see pipes and wrenches.
You are looking at applied chemistry, thermodynamics, fluid dynamics, and spatial geometry, all executed by hand, often in the dark.
It is highly skilled applied physics.
And I think that leaves us with a truly profound thought to carry away today. Every single morning, you walk into your bathroom, you groggily reach out, and you turn a handle. Instantly, water arrives at the exact pressure and temperature you demand.
And we completely take that reality for granted.
But behind that drywall, holding back the immense, relentless hydrostatic pressure of the city water main, are hundreds of tiny, hand-forged chemical bonds. How many beautifully soldered joints, each one a tiny, unseen victory of heat, precision, and metallurgy, are quietly holding your daily life together right now? It is a hidden, perfectly sealed architecture that we rely on every single second, and it only exists because someone knew exactly how to master the flame. Thank you so much for joining us on this deep dive. Keep exploring the hidden mechanics of your world.